Today I am going to discuss the unbalanced assignment problem. This is a 6 by 5 unbalanced assignment problem. 6 jobs are given and 5 operators are to be allocated with the job. As this is an unbalanced problem because the number of jobs and number of operators are not same, then what you will do to proceed to solve the problem? First of all, what you have to do to make it a balanced problem, to apply the Hungarian method, first you add one dummy operator. This is called dummy operator to make it a balanced problem. I am going to add one dummy operator, say sixth operator. The dummy operator is to be added to make it a balanced assignment problem. And these are the time required to complete the jobs. 1.5 say hour, all are given in hours. If the operator 3 is given the job 2, then the time will be required to complete the job is 1.5 hours. In this way, the times are plotted or noted on this matrix. I am not repeating the logic is same. Okay, I am going to explain another 7. This indicate if the operator 2 is given the job 5, the time required to complete the job will be 7 hours. Now the question is which operator is to be attached with which job so that the total time required to finish all the job will be minimum. That is the problem. As I have already discussed, this is an unbalanced problem because 6 jobs are given but the operators are 5. But to make it a balanced problem, to apply the Hungarian method for solving the assignment problem, first of all, you have to make it a balanced problem. You have to add one dummy operator to make it a balance with 6 by 6. And what will be the timing you will take? You put 0, the time required to finish the jobs. Why it is 0? It is only for mathematical purpose. 0 means as if the work is not practically given, is not being given. But for mathematical purpose, we have to add it to make it a balanced problem. Now, I am going to apply the Hungarian method step by step. Okay, first, what you will do? For each row, you will find out the minimum element and subtract that minimum element to all the remaining elements of the respective row. Say, for first row, the minimum element is 0, so you have to subtract 0 from all the elements. As if you subtract 0, the element remains same. That's why I am not changing. That means 2.5 minus 0 is 2.5. 5.0 minus 0 is same. That's why it is not being changed. Okay. Same process is to be done column wise. If we do column wise, then what will happen? Now I am doing the next step. For first column, find out the minimum element. What is the minimum element in this case? 2 is the minimum element. Out of 2.5, 2, 3, 3.5, from all these elements of this column, the minimum element is 2. You have to subtract 2 from all the elements. As the space is limited, I am using the structure of this cell matrix and change the value on the cell matrix. But in your case, you will definitely do it in a separate page. Okay. So you have to subtract 2 from all the elements of column 2. I have noted here so that I should not forget it. 2 is to be subtracted from all the elements of the column. Then what will be the value? 0.5. This will be 0. This will be 1.0. Subtract 2 means 1.5. This is subtract 2 means 2.0. And this is 4.0. Same process is to be done for column 2. Find out the minimum element of this column and subtract from all other elements. The minimum element is 5. Again, I am noting it 5 so that we should not forget it. Subtract 5 from all the elements of this column. If you subtract 5, that means it is 0. Again, it is 0. 6.5 minus 5 means 1.5. This is 7 minus 5 is 2.0. Again, this is 2.0. And subtract 5 from 9 means 4.0. Now, third column. Same process. Find out the minimum element of this column. What is the minimum element? That is 1. And you have to subtract 1 from all the elements of this column. If you subtract 1, that is 0. This is subtract 1 means 0.5. This is 1.0. This is again 1.0. And this is 2.0. And this is 4.0. Now, fourth column. What is the minimum element? In this case, the minimum element is 6. Minimum element is 6. Subtract 6 from all other elements. That's why it is from all elements 0. 7 minus 6 is 1. 8 minus 6, that is 2. And 9 minus 6, that is 3. 9 minus 6 again 3. And 10 minus 6, that is 4. That is 4. For fifth column, the lowest element is 1. Subtract 1 from all the elements. All the elements, that's why it is 0. And subtract 1 from this, that is 2.0. That is again 2.0. Subtract 1 means 3.5. This is 5.0. And this is 5.0. That is the minimum element of this column, 0. And if you subtract 0 from all the zeros, it will remain same. The row and column operations have been completed. Now, the next process. What is the next process? The next process is you have to draw minimum number of horizontal and vertical lines to cover or touch all the zeros. No diagonal or other type of line is allowed. Only horizontal or vertical lines you have to pass on all the zeros. No zero should be left out. But the condition is the number of lines should be minimum. By minimum number of horizontal and vertical lines, you have to attach or cover all the zeros. In this case, suppose I am drawing this line 1. Next, this is also another line, and this is another line. I think all zeros have been covered. No zero have been left out. So only 3 lines have been used here to cover or attach all the zeros. The condition for optimum or minimization is this number of lines must be equal to the order of the matrix. What is the order of matrix in this case? In this case, the order of the matrix is 6. Because 6 rows, 6 columns, the order of the matrix is 6. But the number of lines required to cover all the zero is 3. That means we have not reached to the optimum. Then what you have to do? The next you have to do, if you find out the minimum element from the remaining elements which have not been covered or touched by the horizontal or vertical lines, and you subtract that element from all the remaining elements. Remaining elements means all the remaining, not this, remaining elements. You subtract that lowest element from all the remaining elements. Is it clear? Another thing, what you will do, and add that element to the junction point, horizontal line and vertical line, where it is crossed junction. Here you have to add that minimum number. The rule is same. I need not to do anything to other elements, which has been, that means you need not to do anything on these. It has been touched. It will be remain same. But you have to add here junction point, but not here, not this way. So the rule is same. What you have done earlier, the Hungarian method, that same rule is being applied. Only the structure or dimension of the matrix is more. Again, I am using the same matrix structure to save the space. What is the minimum element from the remaining elements? One, these. What is the minimum element? You see, I will use this structure, but positively you do it in a separate page in your copy in exam. Otherwise, it will be complicated and it is not allowed. The minimum number of the remaining element is 1.0. 1.0. So first, I am subtracting. I am using different color to avoid the confusion. So I am subtracting this minimum element from all the elements. So you have to subtract 1.0 to 1.0. That's why it is 0. This is subtract 1. That's why it is 0.5. Better it is to be written 0.5 in different color. 1.0, that is 0. 2 minus 1, that is 1. 2.0 minus 1, that is again it is 1. 1.5 minus 1, that is 0.5. 2 minus 1, that is 1. This is 0. This is 2. And this is 3.5 minus 1 means 2.5. Minus 1 means 1.0. This is again 1.0. This is 1.0. 3 minus 1 means 2.0. 5.0 minus 1 means 4.0. This is 3.0. This is 3.0. This is 3.0. 3.0. This is 4.0. This is 3.3, 4.4. Acha. These will remain same, but the junction point it will be added as 0 plus 1. 0 plus 1. That's why it will be 1.0. The reverse table. Is there any junction? Here is also a junction. That's why again 0 plus 1 means 1.0, and all these will remain same as the lines have been passed over the 0. That's why 0.5, whatever it be, you should write it. 0, it will not change. You have to do nothing on this. 0, and just erasing. This will be the revised matrix. 0, and this is also 0. Here this is 0. This is again 0, and this is also, this is also 0. 0.5, it will not change. 0.5, and that will be 1. It is 1, and this is 2.0. No change. Again, this will also not change. All are zeros. That's why I am writing 0. Putting 0 here. 0, 0, 0, and 0. I am utilizing same structure to save the space. This will be the revised matrix after doing the process. Now what you will do? Again you will pass horizontal or vertical lines so that minimum number of lines will cover all the zeros. Okay. Now, how you will do it? Suppose I am passing one line this and over this one line this. Next, you can pass a line this to cover this. You can also pass a line to cover this, and finally we'll cover a line this. I think all the zero have been touched by the horizontal or vertical lines. No zero is left out. Now see how many lines you have used to cover all the zeros. 1, 2, 3, 4, 5 lines. You have used 5 lines to cover all the zeros. Have you reached the optimum? Is it equal to the order of the matrix? No. Why? The order of matrix is 6, but the lines required to cover all the zero is 5, is less. This means again you have to proceed further. You have to repeat the same process we have done just in the previous process. What you will do? You find out the minimum element from the left out element. These are the left out elements. From this, the minimum element is this one. You have to subtract 1 from all the elements, and you have to add this minimum element to the junction point. You have to add here, you have to add here, you have to add here junction point, and the other elements will be remain same. Then what will be the next matrix? 1 is the minimum. That means I am writing this is 0, this is 0, this is 1, 2 minus 1, minimum is the 1, again this is 1, and this is 2.0, this is 1.0, and this is 0, this is 1.5, 1.5, and this is 3.0, and this is again 3.0. This will be remains same, it will not change, but here you have to add this minimum number. That means this will be 1.5. I will draw a next fresh matrix, and this will be 0.1 means this is 1.00, 1.0, sorry, and again this is 1.0. You have to add it here, and again you have to add it here. That means it will be 2.0, and this will be remain same. It will not change as the line have been passed over this. This will be the revised matrix. Now I am drawing a revised matrix 1.5, 1, 1, 0, 2.0, 0, 0, like this. To avoid the clumsy or complicacy, now I am erasing this matrix and drawing a fresh one. Drawing a fresh matrix for next process. Because if I write over it again, then it will create confusion. As the minimum number of lines passes over the zeros are less than the order of the matrix, that's why you have to proceed further. So what we have to do? We have to find out the lowest element from the remaining elements. That means which elements are not covered or touched by the horizontal or vertical lines, and that will be added to the junction of the horizontal and vertical lines and subtract from the remaining elements. But the numbers which are covered on the lines should remain same. After doing that operation, we will get this matrix. Okay, and again same as previous process, try to pass horizontal and vertical lines so that all the zeros are covered. But keep in your mind, the number of lines should be minimum. You should not draw at random. So try to pass minimum number of horizontal or vertical lines to cover all the zeros. In this case, these lines will cover these zeros, and these lines will cover these zeros, and also pass a line, these three lines and one lines you have to draw to cover this, and to cover all these you have to draw another lines. I think these are the minimum lines by which you can cover all the zeros. Now check how many lines. 1 2 3 1 2 3 1 2 3 lines, 4 and 5 lines. That means 5 lines are required to cover all the zeros. That means you have not reached to the optimum. The condition for reaching the optimum is the number of lines should be equal to the order of the matrix. In this case, the order of matrix is 6, but the minimum number of lines touches to cover all the zero is 5. That's why we should proceed further. What is the rule to proceed? Next step, the rule is same. That means at the junction point, you have to add the lowest element. The lowest element of the elements which are not covered by the horizontal or vertical lines is 1. You can see 1, 1, 1. The lowest element is 1. So what you have to do? You have to subtract this lowest element from all the remaining elements. And what you have to do? And you have to add that number to the junction point. This junction point, where the horizontal and vertical lines have been crossed, and the elements where the lines has been passed, you need not to do anything. It is better to draw through another color. So in this case, the lowest element is 1. That's why I am doing on the same matrix, but you will do in a separate matrix. That is 2.5 minus 1 is 1.5. 1 minus 1 is 0, and 3 minus 1 is 2, and this is 0. This is again 0, and this will be 3 minus 1, that is 2, and this is 0. This is 0. This is also 0. This is 1. This is 1, and this is 0.5. This is 0.5. This is 2. 3 minus 1 means 2, and 3 minus 1 means 2. All these are the remaining elements, and you have to add the minimum element to the junction. Where is the junction? Here is the junction. That's why here you have to write 1. 0 plus 1 is 1. 0.5 plus 1 means 1.5. I will draw a separate matrix, and it will be better. 0 plus 1 means 1. And another, this is the cutting point. That's why in this place it will be 3. 2 plus 1. And this will be 1 plus 1 means 2. And this is also 0 plus 1. And next matrix will be, and that will be remain same. It will not change. It will not change. That means 1.5, 1, 1, 0, 0, 3, 0, 0, 1.5, 0, 0, 2, 1.0.05, 1, 0, 0. In this way, it will be just, it is better to check it, and it will remain same. Revised matrix will be like this. The revised matrix, I am writing this matrix in a fresh way. I'm writing the same matrix. I'm writing this matrix in a fresh table. In a fresh table, it is better. Otherwise, it will be clumsy and it may create problem. So 6 by 6. This is 6 by 6 matrix. 6 by 1, 2, 3, 4, 5, and 6. And 1, 2, 3, 4, 5, and 6. And the values will be, what are the values? 1.5, 1.5, 0, 0, 0, 0, 1.5, 0, and 2. 1, 0, 1, 0, 0.5, 0.5, 0, 0, 2, 0, 0, 2, 1, 1.51, 1.5, 1, 0, 1, 1, 0, 1, and 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 1. And 0, 0, 0, 0.5, 0.5, 2, 2, 2, 2, 3, 2, 1, 3, 2, 1, 0, 0, 0. Again, you have to pass horizontal and vertical lines to cover all the zeros. And the rule is the minimum number of lines you should use to cover all the zeros. Now, try it, how you will do it. Minimum number of lines. You see, this is this one to cover all the zeros, and also this one. This line is also required, and this and this. That means 6 lines are required to cover all the zeros. I think it is not possible to cover all the zeros less than 6 number of lines. That means the order of the matrix and the total number of horizontal and vertical lines, in this case all are vertical lines, you can draw in different way also. You will see that is also 6. That means we have reached to the optimum. The process of finding the optimum table has been completed. Now we have to move to the next step, next process. The next process is allocation. Allocation of job with the operators. The allocation of job with the operators. I will do it. For that, it is better again to draw the fresh table. The same table I will write fresh way. You will also do it in a separate page. Otherwise, this line, horizontal or vertical lines, will create problem for allocations. That's why, though it will take time, but it is required. Otherwise, it will be problem for you to allocate. I will show you how we will allocate it. Now, this is the optimum table where you have to put the allocation. 6 by 6. Final table will be this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Just fresh way I am writing the last table. 1.5, 0, 0, 0, 0, 1.5, 0, and 2. 1, 0, 1, 0, 0.5, 0.5, 0, 0, 2, 0, 0, 2. 1, 1.5, 1, 0, 1, 1, 0, 1, 3. 0, 0, 0, 0, 0, and 1. 0, 0, 0, 0, 0.5, 0.5, 2, and 2. 2, 2, 3, 2, 3, 2, 1, 0, 0, 0. Okay. This is the table. Now, 1, 2, 3, 4, 5, 6. 2, 4, 5, 6. This is 1, 2, 4, 6. Suppose this is the jobs. Suppose this is the jobs. This is the operators. Operators. Okay. Now, how will proceed for allocation? As I have already mentioned in my previous video, if there is any row or column where only 1 0 is available, then you allocate that, because you must have to allocate that job. and at the moment we are allocating this, you must have to cross this, because you cannot further allocate operator 6, because 6 job is allocated to operator 6, and that's why we have crossed it. Now start allocation from this side. Suppose this is, you are taking this one, at the moment you are taking this, that means you cannot allocate. Why I am doing cross? Because once you have allocated this job to with the operator 4, then it is not permissible to allocate to any other operator, because it is already booked. That's why others are 0, crossed. In this way, similarly, this operator has been allocated to this job, that's why all allocation will be crossed. Now say this, if you allocate this, then again this will be crossed, you cannot allocate, and move further, and this is third row and no other 0 is there. Now for this you allocate here, then you cannot allocate this. But say in this case there is no allocation for this job, there is no 0 in this row available. That's why what you will do, you have to change this allocation. You have to change this allocation to allocate here, not here. Okay, that means you cross this, at the moment it will be, that means it will be crossed and there is no allocation. And in that case, if you are allocating this one, then in that case you have to allocate this one. That manipulation you have to do. You check carefully, then it is not very tough, you can do it. Why I am changing it? Because if you put allocation here, then what is the problem? When it is crossed, no allocation is possible for this job. That's why I have changed it and I have kept it here, and there is no problem. In this way you can find out the allocation, and I am writing the allocation as the space is very minimum, that's why no problem, I am writing this side. What is the final allocation? So first job is to be allocated, job 1 is to be allocated fourth operator. Second job is to be allocated, to first operator, and third job is to be allocated with fifth operator, and fourth job is to be allocated, third operator. Fifth job is to be allocated to second operator, and sixth job is to be allocated to sixth operator. And what will be the time, required time? As it is given in the first table, you have to take the value from the first table. You see the first table 1 to 4. 1, for this is the first table. First job, if is allocated to fourth operator, the time is 6 hours. This is hours. If second to 1 is 2 hours. Third to fifth means how much? Third to fifth is 3 hours. Fourth to 3, fourth job is 3 is 2 hours. Fifth to second means, what is the time? Fifth to second, 7 hours. Fifth to second, and 6 to 6 is 0. What is the total minimum time? 6 20 hours. This is the minimum time. This will be the answer. That means the best allocation for this assignment problem will be first job to be allocated to fourth operator, second job to be allocated to first operator in this way, and the total time required will be 20, and that will be your answer. After doing this, you again check, is there any alternative solution also? One thing, if you change the allocation, then you will see the total time will be more than 20 hours if it is not optimum. But sometimes you will see that in different combination also the minimum time 20 hours will be right. You will get 20 hours. Then that is the case of multiple solution. That means in that case the another allocation of jobs with the operator is possible, where the time remains same as minimum 20 hours. That I am going to show you it available here or not. For this, it is better to erase this one so that I can use the same table to see where I have. It is better to erase all the which elements I have used. That's why I'm going to change it for finding is there any other allocation or not with the help of same optimum table. Okay, the same table I am going to use. Further table is this 1.5 1.5 0 0 0 0 1.5 0 2 0 2 1 0 1 0 0.5 0 0 2 1 1.5 1 then 0 third 0 1 and 3. This is 1 and 3 0 0 0 0 0 0 0 0. Same table, same matrix table is being used to check whether there is any multiple solution is available or not. Multiple solution means the combination of jobs and operators is different, but the total hours remains the total minimum hours it will be remains same. Then we can say it is a case of multiple solution. This is the optimum table. Again, I am going to check is there any alternative solution or not. Achha, this row has only 1 0, that's why I am going to allocate it first. Achha, previous in the case of previous allocation I had taken this one, but now I am changing that allocation of the first row to this one to check is there any alternative allocation or not, because it is not possible to allocate any other person, that's why it's crossed. Now say I'm taking this one, then this will be 0 0 and 0 0. Now third row, if I allocate this, then 0 0, and next if we allocate 0, this is 0, that will be possible. If we allocate this is 0, and that will be the fifth row. But it is not possible, sorry, when I allocate this, you should cross it. You should cross it. Some mistake, this mistake I already made, because at the moment I allocate it, no vertical or horizontal 0 is allowed, cross it. But one thing you check again, no allocation is available for fifth job. That's why I have to change it slightly. What change will be? You, by inspection, you can see you not crossed it, you allocate it here. If you allocate it here, then it will cross, no, and this 0 will be available. That's why in that case, you take this one. It is possible, there is no problem. And you can check this is the revised allocation. Now I am going to show whether the total required minimum time is again 20 or not. That I am going to show. This is another allocation. This is another allocation. What is the revised allocation? First is 5. Number 1 job is allocated with fifth operator. Second job is allocated to first operator. Third job is allocated. Third job is allocated with fourth operator. And fourth job is allocated with third operator. Third operator. Fifth job is allocated with second operator. Second operator. And sixth job is operated with sixth operator. Now what will be the timing? You check first job with the first operator. What is the time? How much time? 1 for fifth means 1 hour. And second to 1 means 2 hours. Third to fourth means 8 hours. 8 hours. Fourth to 3 means 2 hours. This is 2 hours. And fifth to 2 means 7 hours. 7 hours. 6 to 6 means 0 hours. The total time again it is 20 hours. That is, this allocation of jobs with operators are also possible, and this also represent the same minimum time 20 hours. Hence, this is a case of multiple solution. Multiple solution means In this case, two types of allocations are possible by which the minimum time required to complete all the jobs is same, which is 20 years. This is all about how to deal, a how to solve an unbalanced transportation problem. Though this is a slightly lengthy problem, but the process is same. If you do it carefully, then there is no problem, and you can reach to the conclusion. Thank you. If you have any problem, please write to the comment box. I definitely will reply at the earliest possible. Thank you. Thank you very much.